Welcome to our first lesson on pulley systems. Okay, this is just under machines. Okay, so your attention should be on mechanical advantage is load over effort, velocity ratio is distance moved by effort over distance moved by load, and then efficiency is work output over work input times 100, or mechanical advantage over velocity ratio times 100. Then many students have failed to grasp the technique, the explanation behind the two graphs in the simple machine. One, mechanical advantage over load, and also efficiency over against load. Efficiency against load, it rises gradually, not linearly, but at some point it tends to stabilize as an horizontal line, but not at 100%. So I want to try and explain about the reason behind this and the reason behind this graph. So for that reason, I'll just give a kind of data to help me achieve that. And before I go to my data, I want us to concentrate down here. We understand a few things. This diagram here has velocity ratio 2. This one has velocity ratio 2. This one has velocity ratio 1. And this has velocity ratio 3. Okay? Now, velocity ratio is very important in justification up there, just for you to understand. Justification is very important. Now, the major thing we attribute to this graph reaching a level and trying to be horizontal is because of two things. Whatever input you do to make the load move, unfortunately, there will be two things for you to overcome. One, friction, and two, the weight of the lower pulley. Again, if we focus here again, we focus down here for me to explain. Yes, this will be movable. So the weight of this pulley and this I've added. Do not think it is only this load you will be lifting. As you lift this load, there is this pulley which will be moving. Then there will be friction. So ideally, do not concentrate on the load, but at the back of your mind you must have the lower pulley will be moving and friction will operate. If we come here, you will find friction at this, where the rope is going around the pulley. There will be friction, but this pulley does not move because it's a fixed pulley. One pulley can be fixed or can be movable. Single fixed pulley, movable pulley. Here velocity ratio is 2, so you have both the friction here, and then this pulley has to move as you pull the effort. You place the effort here. As you pull it, this moves. So those two are basic reason. Those two are basic reason why we cannot have efficiency against load graph to continue arising. At some point, it stabilizes. Again, we are not doing the study of this in totality, because when the load becomes very, very, very big, things change. The graph is not the same. It's not. But we only chop a part of graph work vis-a-vis pulley system that you are able to follow and comprehend. And that's what I'm going to do here now. So I've given some arbitrary figures that let the weight of the lower pulley be 100 Newton. So as we increase the load, it does not change. So get things right. It does not change, because that pulley will have the same weight, whether you increase your load or reduce. Get it right? So I've said, let us imagine it is 100, 100, 100, 100. Then the load, what we put here. Now, again, I focus down. We focus down a bit here so that you see. This is the load. So I can put 100 Newton. After that, 200. After that, I change to 300. After that, 400, and so on. So what we place here can be changing, but the weight of this cannot change. Once we say it is 100, it is 100, irrespective of what we place here. Okay? Right, we come back. So I have weight of the lower pulley is fixed. The load can be changing. I can be putting different loads. Now I want you to start from here. I've written here, what would be energy to lift the lower pulley? If the lower pulley is 100 Newton and the load we placed is 100 Newton, then your energy is divided 50-50. 50 is used for this and 50 is used for that. So I've written here, energy to lift the lower pulley is 50% and the energy to lift the load is 50%. Okay? Suppose I have added now, my load is 300, but the lower pulley is still 100 because it does not change. So look, how do I get this? What is the energy to lift the lower pulley? If the lower pulley is 100, the load is 300. Then I take 100 over the total, which is 400, times 100, I get an idea of percent. Okay? I get, this is the lower pulley, 100 newtons, over the total. Because we have this and that. This is the load in quotes, the lower pulley. The load we placed, which we are supposed to raise, is 300 newtons. So what part of my energy will go to this? It will be 100 over 400 times 100 to get a percent of 25. Automatically, here, it will be 75. You don't need to do that. 300 over 400 times 100. So I'm trying to give you a picture of partitioning of your energy. This much energy goes to overcome that. This much energy goes to overcome that. Okay? So the energy, I shall deal with it later. So I want you to get that system. Okay? Here. Now, the load I'm dealing with is 600. But the weight of the pulley is 100. So to know what percentage of my energy goes to overcome this and what percentage goes to overcome this, I'll do simple percentage. 100 over 700 times 100, which gives you 14%. Now once I get 14%, I subtract from 100, I get 86. Or if you started with this, you would do percentage of energy going to lift the load is 600 over 700 times 100. You get 86%. But we know percentage is 100. So the balance, if I had started with 86, I don't need to do this calculation. I just take 100 minus 86, I get 14. Lastly, suppose my load is now 900. It does not change the weight of the lower pulley. So what are the percentages going to overcome the lower pulley to overcome the load? The lower pulley, what percentage is going to overcome the lower pulley? 100 over 1,000 times 100 to get percentage, which comes to 10%. Then the part of energy to overcome the load will be 90%. Again, you can see the trend. Once I get this, I can get this. Once I get this, I can get that, and vice versa. So you can see, it's very important to know that as the load increases, the energy to lift lower pulley decreases. Okay, it decreases. Now, what else do I want you to know? I'm going to wrap this, and then we do a few counter-checking questions here. Okay? What I want you to know, the lower pulley here, this lower pulley is 100 because it has to move. It is there. Whether you use velocity ratio 5, 8, and so on, it is there. So one thing I want you to know, maybe two things. Let us assume velocity ratio is 3, which is distance moved by effort over distance moved by load. Okay? So this implies ratio 3:1. When the load moves 1 meter, the distance moved by effort is 3 meters. This is very important because we are going to handle this. But in a nutshell, look at this. Once you have understood that, just look at this. Suppose we put this 100%. What would be the meaning? Put it in red so that you get. Suppose this is 100%. What would this mean? It would mean this is 0 because the total has to be 100. And if this is 0, it means we don't have energy to lift lower pulley. Now, we are told the lower pulley is 100 newtons. And here, when you put 0, it would mean it is not there. You will be contradicting yourself. So in short, the graph cannot reach that level of 100%. It has to be low. Why? Because two things. There is friction we have to overcome and the weight of the lower pulley. The weight of the lower pulley has to come into play. It adds to our load. Okay? So it cannot be 100%. So I'm going to continue. I want you to get this first and study it. Then, this I've added here as energy required, okay? I will redraw this next time as I pump in now the real stuff. For now, I want you to understand the graphs cannot be the E against L, efficiency against load cannot be 100%. Two reasons we give: friction in the moving parts and the lower pulley adds to the load. Those are the two reasons. But for you to understand so that you can explain to another person, I will have to do it in lesson 2. Remember to subscribe. You get the next. Bye-bye.